Empowered to lead. Wired to learn.
Hello and welcome to Power Test 26 here in Nashville. I'm Ellen Parson, Editor-in-Chief of EC&M Magazine, part of Endeavor B2B, and I'm here with some subject matter experts. They are giving presentations at the Power Test conference, and I'm here to get some key takeaways from their presentations to pass on to our audience with EC&M, the ones that would resonate the most with our audience is what we picked out today. So we have today a couple of those subject matter experts with us. Lee Howard, he is a senior grounding specialist with Hood, Patterson, and Dewar. And we have Jacob Rio. He's a grounding specialist also with Hood, Patterson, and Dewar. And we've interviewed you all before. Great content before. So we're glad to have you back. Thanks for joining us.
Thanks for having us.
So we're basically just going to talk about your presentation. We're going to start with your title because you always have great titles. This year, your presentation is titled Apples to Oranges to Banana Pudding. So we definitely need to get into that, what that means. So could you tell the audience how that phrase would apply when it comes to grounding test equipment? That doesn't seem like a likely title. So tell us about that.
Well, honestly, it was kind of an off the cuff reaction to what should we call the title. We knew we were comparing test equipment, and so kind of an apples to orange thing. But then we also realized there's some of this test equipment out there that really can't even be considered test equipment. So that came into the banana pudding thing. We were including some of that equipment at first, and then we kind of removed it because we were realizing we were kind of poo-pooing the equipment. But there has been times I was given a piece of a test equipment and it barely fit in the palm of my hands, and they were wanting me to test the grounding system for an oil refinery. And I'm like, what am I supposed to do with this? So there's your banana pudding.
Okay, that makes sense. So this is obviously a complicated topic. We're trying to simplify this and give the key takeaways. So if you could tell us, since the grounding systems have an added complexity of residing underground, what are the factors that come into play as far as making the testing more difficult to perform correctly than other types of electrical testing? That's got to be an issue, right? From being underground and all of the different factors that come into play. So what are some of those?
In many ways, because it is hidden and it's underground, we have to understand the size of the grid that we're actually testing. Many facilities we go to may be connected to a generation station or an adjacent substation, and a factor of the testing requires us to know what size the grid is. So we need to do continuity testing to those adjacent stations that are not necessarily part of the scope of work to determine what is the size of the grid. Once we determine the size of the grid, then we know how far we have to go to what's called remote earth, which is where essentially we put our reference for the meter and injecting the current. I should say it's more for the injecting the current. Things like that become difficult. And so then we also need to do continuity testing. And there have been times when we find breaks in the grounding system, but it's buried and they have to go and find where that break is at. So that's part of the testing, is to determine the continuity. And then other things is touch potential testing and step potential testing. That location of that buried ground wire becomes significant in just a few feet off of that. The touch potential and step potential can be quite large. So having an accurate grounding system drawing for our modeling, that helps. But it being buried, that's some of the things that we need to consider, is that how do we know how good it is, and was it built to spec?
There's so much to consider there. So I know in your presentation, you also hit on IEEE standard 81. That was updated in November of 2025. So you talked about how grounding test methods have evolved from the 80s to the 2012 versions, I think you cited, of IEEE 81, to the engineers who we're really talking to here. What's the most important change that the electrical contractors and the engineers need to understand, and maybe what drove those changes? So that's kind of a long question, but if you could kind of go over the key points there.
I'll take the first half here.
Right.
Okay, so 81 can be thought of as the genesis. That's where it guides you on how to test a grounding system, whereas standard 80 might be how to design one. 81 is on how to test. So 81 kind of was the basics. It started off with some of the testing measurements and what needs to be done, but it did not account for, let's say, very complex or large grounding systems. It did not take into account what we need today with complex and modern equipment that really needs to test in below 1 ohm resistance values, and what it takes to do that, what type of equipment needs to do that. So, and then also it didn't account for all the pitfalls that you can have when you're doing the testing. What are the things that are going to account for error? So 2012 evolved from 81 in 1983, and then there was an adaptation of 81.2, 91. And they put those two together. And then in 2012, they also added what's called the computer-aided method, or the computer-based method. This device allows you then to model the system and also then account for things such as EMI and RFI noise interference. It can account for buried pipelines. It can account for a number of things that will adjust the model and or get you more accurate results. So as the standard evolves and the equipment evolves, so goes the standard. So let me give you to my...
Okay, Jacob has some thoughts on this.
So that's from the 83 and 2012 version. But since there has been 13 years and lots of improvements, aging infrastructure and everything else, that we're running into a rock and a hard place with some ways, test equipment has evolved. And because of that, we have shifted to more sites having to be tested as energized. They have reworked certain verbiage and reworded certain things to properly address new testing methods and existing testing methods and their evolution. One of those being, as we'll get to in a little bit, the CIT method. It was in the old version, one of the older versions of 81. It's been rewritten for the new version based off of new equipment that has come out since then. There are other things that, again, existing substations, they're not trying to reinvent the wheel at these sites. One of the other things that they have brought up in this one is aggregate testing. Again, for the engineers, we make a safe assumption for aggregate values, and that allows us to calculate what's safe in a substation. But as our NETA Power World magazine article that we just put out in the spring edition set even shows, those conservative assumptions are more than conservative with these values. And they started to address some of that stuff so that you're not necessarily having to, you have an out, I guess is the best way to put it. You have additional testing you can perform before you start having to dig up and do further remediation. You can do something that does not involve going to dig a trench in the ground in an existing substation. You have another step, another test, another way to try to avoid that.
I wanted to get to the safety discussion. Everybody's in our audience is always safety's at the top of the list of what they, want to know about. So when it comes to grounding system testing, what safety hazards are most commonly misunderstood or underestimated in the field?
So there's kind of a combination there where you said misunderstood or underestimated. So some of the underestimated things would be, because we're testing in a outdoor environment, you have a lot of environmental issues that may happen. And because you're testing in a high voltage environment, those are other types of issues. So for, let's say, safety related to shock and such, this is where you start getting into induced voltages on the test lines. There are typically, if we're in a 115 kV station, we're not subject to it so much. But when we start getting into, let's say, up to a 500 kV or a 700 kV station and above, stringing out our test wire, the voltage gets induced in that electrical field. And there are times when we've been shocked when we touch the end of that wire. So making sure that you have your proper safety equipment, your proper PPE, including the proper gloves and your boots on and such. There's been times even when we go to put in a test probe to do the testing and into the surface of the earth, you'll feel the shock as you discharge. So that's one of the things you really have to consider, let's say, safety wise in regard to shock. Other things that happen is, and it's quite often it's not really thought of, is hypothermia or heat exhaustion. That has been a factor at least once for me at one point in time, the heat exhaustion. And then there are things such as critters. We've come across dead animals. We've come across the unchained dog that is being protective of its home. And so these are all things that have to be considered. So quite often we go on to satellite imagery and try to find out what we're going to be running into if we're going into a residential area at times.
Okay, that's smart. Any other thoughts there, Jacob?
And then there's always the reason why we're there on some sites. We may or may not be told there are issues on site, and we are going to go investigate those issues. We've had sites where they had an event where they had a bus fall to ground and blew a hole in the ground grid. And we came out to go do testing to verify it's safe, and we had found touch potentials in other areas that far exceeded what was allowed for the site. We've had other sites that I came out and did testing, and when I got to site was when I got told that there's 30 amps on the ground grid and they don't know where it's coming from. And one guy got lifted off of a heater that wasn't even connected to anything. So we do run into some of those site issues that no one knows about, that just it's environmental. It's no one thought to tell the testers that this is actually happening, and this is why we wanted you here. They're just, hey, we want you to test this.
So that definitely adds another layer of complexity to things. You have to be ready for anything, it sounds like. So in the presentation, could you go over, you covered different types of testing, follow potential, computer-based ground multimeter testing, and current injection testing. So could we do some pros and cons of each, or when they're applied in real world settings, or does that depend on which vertical market you're working in, which ones you're using? Is it specific to the customer? Do you have historical patterns of what you use, or like how do you determine which method to use?
Okay, so the original, let's say your conventional test equipment, original meters that would have been conducive more, or let's say with IEEE standard 83, the 83 version, that had its time and place. It's not that they're bad now, and they can be used on smaller substations that are isolated and kind of out in the out of urban areas and such. But when you start talking about really large substations and complex sites, and you're in an urban environment and such, we then go to what would be more like the 2012 version, where you brought up the computer-aided method, and that allows us to do computer-aided modeling to adjust for the things that we will be seeing in the field, whether that be an underground water pipe for a fire main, or it might even be sprinkler systems, all types of things. The modeling is very sophisticated, and we can build the site. And then after we do the testing, we can always rerun the model or the results, change the model a little bit, see what it does. Does it improve the error? It is quite sophisticated. So that's the system that I typically will almost always will turn to, whether it's a small site, a large site, whatever it be, it'll work for everything.
So yeah, again, I think as Lee was as we elaborate on it, there's a time and a place for everyone. On super small substations, yes, I think that's where the follow potential would really be beneficial. When you get into these bigger sites, these more urban areas, that's where even the computer-based or even the CIT method would be beneficial. The issue you can run into with the CIT method is, realistically, the CIT method is a offshoot of the computer-based method. You're in some of the test sets do allow you to model everything the same way, but the big difference being that with the CIT method, you're, instead of running a test at a time, you're able to run multiple tests at a time if you have enough experienced personnel on site. And that's where the biggest con that we have come across with the current injection is the cost.
Oh, yeah.
The other big difference between the two that they push is, and you can do either, is you could do overhead or you can do overland with your current return. Overhead means you're taking a transmission line out of service, grounding a phase, and using that as your conductor versus just running the conductor over the ground, through the woods, in the road, something like that. We've had I've broached this subject up with several of my clients who have asked if there's easier ways to do the current return. And I get the same comment from everyone, where as soon as I say you have to bring a transmission line out of service, they start having issues. One of our other clients has switched to this method, and they had also reported that because of the increased personnel on site, the increased personnel to do the line outages that would require that were considerably more expensive than using, for example, the computer-based method, which was their original standard before they had shifted. But again, everything has its pros and cons for every site.
Okay. So although the stated intent of the 2025 revision, you went over this in your presentation, is to reduce grounding testing costs, you suggest it actually could increase them. So could you explain that, why, and what should our audience realistically expect moving forward?
So the difference being is when we've done the computer-based method, we'll either do it with one of our assistants or we will have a client provide an assistant, versus if you were to do the current, the CIT method, which is the current ejection method, where you're specifically doing multiple tests at the same time. In theory, while you may be less time on site, you now, instead of having an assistant and a tester, you're now having at least 2 testers plus 2 assistants to help the testers out. So you're running into increased manpower on site, let alone that both the CIT methods, the CIT method heavily prefers using the overhead method. So now you have to get line crews involved because now they have to take this line out of service now. But this isn't taking it out of service at one site. This is taking it out on both sites. Now you're in 2 different substations. You're at a transmission line where you've grounded it. So there's increased costs on both sides of this. And then from a time perspective, that may or may not shave enough time to make it enough of a time difference on site to be cost effective. There are sites that no matter what you do, that there are sites that it's just going to take us, it's going to be time, depending on how far involved and in depth you want to get, depending on what site kind of conditions you're working around. There's always added costs. What we have kind of figured out is the most amount of lead time we can get. The not doing it in the middle of winter, because we have done it in winter. It just, being able to do it in less urban environments also helps reduce the cost. If you start having to go down all these side streets trying to figure out how to run this, not only do we have more of a cost from a testing perspective, but we have more of a cost from a design perspective to try to mitigate all those potential interferences.
Yeah, just one final thing, because quite often we've run into testing and you have the thought of the fall of potential test, and people always think that this is going to be the cheapest method. Now, if you do it what's called the 62% rule, well, yes, you're probably going to be a cheaper cost because they put out the wire, they go hopefully the proper distance, at least 5 times the diagonal size of the grid, but then they just go to 62%, take a reading, and they think that's it. But that's not the proper way to do the test. You have to actually develop the curve based on basically either doing a measurement every 10th of the distance, or even every 20th. And then you see if a proper curve develops. When you get the test done, if you just do 62%, you get a number and you have no idea what it is, because there is, when you think about it, that current wire at that distance becomes like an antenna. And you have all the radio frequency interference, the EMI, the electromagnetic interference. You have no idea what your signal to noise ratio is. So it may be a number, you may get it done cheaply, but you really can't. I know I can't trust the data.
Okay. I think that's a great place to stop. Good advice there. And thanks for trying to make this really complicated subject easy for everyone to understand. So we really appreciate Lee and Jacob being here with us today. Thank you for joining us and for sharing your expertise with our audience. We're here at Power Test 26 in Nashville, and signing off here.